In our look at random variables, we're now going to look at a particular type of random variable. And this first type is called, and it's a discrete random variable, and it's called a Bernoulli random variable. So, a discrete random variable is a Bernoulli random variable if the following properties are true. So, the Bernoulli random variable can only have two possible outcomes, okay? So we can't have more than two. So it's got to have only two outcomes. One outcome is classified as success, and the other one can be classified as failure. So when the outcome is a success, then the value of the random variable is 1, and when it's failure, then the outcome of the random variable is 0. So Bernoulli random variable, two possible outcomes, success gives us a 1, failure gives us a 0. So they're the values of the Bernoulli random variable that we can have. Now the probability of success we call P, and so then the probability of failure, well, there's only two outcomes, so it must be 1 take P. It's got to be the rest of the probability that is associated to failure. So a Bernoulli random variable is fully described by the probability of success, which is equal to P. So as long as we know the probability of success, we know everything we need to know about a Bernoulli random variable. And three things that we might want to know, or two things mainly, are expected value and standard deviation. So the expected value is equal to P. Variance we don't really need to worry about. And then the standard deviation is the square root of P, 1 take P. So notice, as long as we know P, then we know expected value and standard deviation. Okay, alright, so how can we prove these? Well, let's draw up our distribution if it's a Bernoulli random variable. So we've got x, the values, and we've got the probabilities of the values. So the probabilities of a Bernoulli random variable are either 1 or 0. The probability of a 1 is P, that's our probability of success. The probability of 0 is 1 take P. So if I'm working out expected value, it's going to be 1 times P plus 0 times 1 take P. 1 times P is just P, 0 times anything is just 0, so it's P plus 0, which is P. So that shows us the expected value of this variable is P. Now for the standard deviation, I'm going to do it as the sum of the values squared, so it's going to be 1 squared times by P plus 0 squared times by 1 take P, and then we're taking away the mean squared, so we're taking away P squared. Okay, so then it's the square root of 1 squared times P, so that's just P. 0 squared times 1 take P is just 0, and then we're taking away P squared. Okay, alright, so I'm going to take P out as a common factor. So obviously the 0 term isn't there, but P, take P squared, take out P as a common factor, I get left with 1 take P. And so that's the proof of my standard deviation being the square root of P times 1 take P. Okay, alright, so what's some examples? Well, let's take this one. A pen is randomly selected from a box containing 7 red pens and 3 blue pens. Let x be 1 if the selected pen is red, and x equals 0 if the selected pen is blue. So we've got to explain why it's a Bernoulli random variable. First thing to say is that there's only two outcomes. So we can either get a red pen or a blue pen. So x equals 1 for one outcome and x equals 0 for the other. And that is enough to say that this is a Bernoulli random variable. So there's got to be two outcomes. The value of one of them has to be 1. The value of the other one has to be 0. So we've got to find the mean and standard deviation of x. So expected value of x is a probability of success, which we call p. Now success was getting a red pen. So 7 red pens out of 10 is our probability of success is 7 over 10 or 0.7. So that's our mean. Now, our standard deviation, well, as long as we know our probability of success, we can work it out. But just to draw up the distribution, so it's xi, probability, 1 was getting a red pen, 0 was getting a blue pen, so let's just write that in. Now I could have also said that x is the number of red pens I have after taking one pen out. So if I pulled out a red pen, then the number of red pens I've got is 1. If I pulled out a blue pen, then the number of red pens I pulled out was 0. That's another way of describing the same random variable. Now, probability of getting a red pen was 7 out of 10, so it's 0.7. Blue pen is going to be 1 take 0.7, which is 0.3. So then, the standard deviation is the square root of 0.3 times 0.7. So it's the square root of 0.21, and that is equal to 0.458. Okay, a more, I suppose you could say it's a more practical example. So scratchy tickets are one form of legal gambling. A panel is scratched off to reveal if the ticket is a winning ticket or a losing ticket. A very large number of tickets make up one batch. Suppose that 1 in every 4 tickets in a batch is a winning ticket. So define a Bernoulli random variable and give its distribution. So we want to define it in such a way that we actually get 1 being success and 0 being failure. So let's say upon drawing one scratchy ticket, let x be the number of winning tickets drawn. Now, the idea here is that we're only drawing out one ticket. Now, if that's a winning ticket, then the number of winning tickets we've drawn out is 1. If that's not a winning ticket, then the number of winning tickets we've drawn out is 0. So we've set up our Bernoulli random variable in such a way to make 1 success and to make 0 failure. So I've got to give the distribution. So values and probabilities. Values will either be 1 or 0. So what's the probability of drawing out a winning ticket? Well, 1 in every 4 is a winning ticket. So 1 over 4 is the probability of getting 1 winning ticket. The probability of that not being a winning ticket, therefore, is 1 take a quarter, which is 3 on 4. So notice how I set up my Bernoulli random variable. So 1 represents, or 1 is success, and 0 is failure. Okay, now you might actually remember this particular example. So between 2008 and 2010, a number of animals were used to predict the results of international football games. The best known was Paul the octopus. To make a prediction, he was presented with 2 parcels of food marked with the colours of the competing teams. The food he ate first was taken as his prediction. Now, these were elimination football matches resulting in a win for one of the 2 teams. Assume that he selected his parcel of food at random. Now that's really key, that sentence. So that means that the probability of success, him actually getting the right team, is 0.5. So I've got to define a Bernoulli random variable and give its distribution. So again, in this case, I want to define it in such a way that the only two values are 1 or 0, and 1 represents success and 0 represents failure. So I'm going to say let, or let's say upon pull, selecting the winning team, from one match, let the number of winning teams, or let X be the number of winning teams he selected. So if he's selecting the winning team from one match, he can either get it right, and so he's selected one winning team, or he can get it wrong, and so he's selected no winning teams. So the only possibilities are 1 or 0. Probability of him selecting the winning team, well, that was at random, so it's a half. Probability of selecting the non-winning team is also a half. Okay, alright. So, in question 4, we've got to calculate the standard deviation of both these two examples. So, question 2, so the mean, so example 2, the expected value of x is, well, that's the probability of success, so it was a quarter. Remember, that was the scratchies ticket. The standard deviation is a quarter times 3/4, so it's the square root of 3 on 16, so that's the square root of 3 over 4. For example 3, well, the expected value of x was a half, and then the standard deviation will be a half times a half, so the square root of a half squared, so it will be a half. Now, we've been asked to consider the original definition of standard deviation, explaining why example 2 has a smaller value. Well, in this case, although we have the same range, we don't have the same mean. So it's kind of hard to compare. Or is it? Well, our expected value is a quarter for the first one, so that's closer to 0. Now 0 is a more heavily weighted value. So remember that our standard deviation definition says it's a square root of each value, take the mean squared, multiplied by the probability. So for example 2, we can say that the mean is closer to 0, so, and 0, so it's closer to 0, the value with the greater probability. Whereas in example 3, mu is equidistant from both values which have the same probability. So we would expect example 2 to have the smaller standard deviation. And let's just check that. So half is 0.5 and then root 3 over 4. I'll just get the decimal approximation for that. Is 0.4433. So it does have the lower standard deviation, which is what we expect from what we just said. Okay.